We're going to practice some buffer weak acid strong base titration calculations. Now, what I'm going to start with over here, we're going to calculate the initial pH of this acid solution before any base is added. We're going to find the volume of the base required to reach the equivalence point, and these two things are things we have done before. This is simply stoichiometry. Stoichiometry was covered in Chemistry 1. The initial pH of a weak acid solution, well, that was covered in the previous module, the weak acid module, so we know how to do this as well. This is the part that is new. So the pH after a little bit of base was added at 1/2 of the equivalence point. Well, first you have to know what the equivalence point is, and then pH at the equivalence point. So let's get started here. We have a titration that is 24 milliliters. I'm going to start writing this over here. So 24.0 milliliters of a 0.105 molar acetic acid solution. That's the only part I'm going to be concerned with to get these two pieces. So we need the Ka of this weak acid. Well, the Ka is 1.8 times 10 to the negative fifth. We're going to need that a couple of times. So write it down somewhere where you have it. When there's no base added, this is just a weak acid problem. So we just need the initial concentration of the weak acid. We have no acid and no conjugate base, no A minus. So we need to change this. This is an equilibrium. So we're going to take away some amount of weak acid. We're going to add some amount of H plus and some amount of our conjugate base. So at equilibrium, our concentrations look like this. This should be old hat by now. So the Ka is going to be 1.8 times 10 to the negative fifth, and that's acetic acid. That's why I know that. And I looked it up and popped it somewhere around here. Here's acetic acid, 1.8 times 10 to the negative fifth. Let's move this back. And let's set up that equilibrium expression. So I have my x's on top, my concentrations of my product. So that's going to be x squared divided by the concentration of the reactant, which is going to be 0.105 minus x. So the question is, can we simplify? Well, is the initial concentration more than 1,000 times different than the Ka value? And the answer is yes, it is. So we should be able to simplify. To simplify means we're going to ignore this x because it's going to be relatively so small compared to that initial concentration that the initial concentration will not be seen as changing. So now we solve for x. So we multiply by the denominator, 1.8 times 10 to the negative fifth times 0.105, and I get an error because I put it in my calculator wrong. And I get that x squared is equal to 1.89 times 10 to the negative 6. So I need to take the square root of both sides and get an x value is equal to 1.37 times 10 to the negative third. So x is the concentration of the hydrogen ion, which is 1.37 times 10 to the negative third. The unit is capital M molarity. So now I can find the pH. Now I can solve for the pH. So if that's the concentration of my hydrogen ion and pH equals the negative log of the hydrogen ion, then I take the log of that value and I get a pH is equal to 2.86. So that answers A. Let's go back over here. So the initial pH is 2.86. So what is the volume of added base required to reach the equivalence point? Well, we need to know the reaction. And this is a reaction, this is acetic acid, so CH3COOH. This is the acidic hydrogen. These hydrogens do not play with the acid-base reaction. So this is going to be a 1-to-1 when we go NaOH. What that means is 1 mole of acetic acid reacts with 1 mole of sodium hydroxide in order to form water and the associated salt. Now, the associated salt is the cation of the base and the anion of the acid. So here we have sodium, and then we would write acetate. You could write it like that. You could write it with the Na over here if you really wanted to, but let's keep things consistent and have the Na on the left. So we have our chemical reaction. We have a 24 milliliter sample, so I need to start with that volume because I'm going to start with my acid here. So a 24 milliliter sample of my acid, and I'm going to multiply that by the molarity, 0.105 moles of acid per 1 liter of acid. Remember, that is the definition of molarity, moles of solute divided by liters of solution. And then I need to convert those moles of acid into moles of base. And I do that by using the stoichiometry found in the balanced chemical equation. So the absence of a number here in front of these chemicals is not 0. The absence of a number means that it is 1. So there is 1 mole of sodium hydroxide that reacts with 1 mole of acid. Now, the question is, what's the volume? And I have the molarity of my sodium hydroxide, so I can use that molarity as a conversion factor. 0.130 moles of NaOH per 1 liter of NaOH. And I just run through this arithmetic. So that means I multiply everything across the top. 0.24 times 0.105 times 1 times 1, divided by the product of the bottom, which is 0.130. So I get that I should have 0.01938, and I gave you too many significant figures on purpose, liters of sodium hydroxide. So now let's analyze this for sig figs. We have 3 sig figs in each of these quantities, so I should end with 3 significant digits as well. So I would declare this 0.0194 liters of sodium hydroxide. Now that's 19.4 milliliters. So if I've added less than 19.4 milliliters, then I'm not to the equivalence point yet. So that'll give us some idea of which method we need to use. Well, what's the pH at 6 milliliters of added base? Well, now we need to compare moles. So we need to take the volume of the acid in liters times the molarity of the acid, which I have already forgotten, 0.105. So that is moles per liter, and that will give us the moles of acid that we start with. So now we need to find out, well, how many moles of base did we add? Well, it was 6 milliliters of a 0.130. So 6 milliliters, and I know that these sig figs, I know I just dropped a bunch of sig figs there. 30 moles per liter. Do this multiplication, and I get 0.00012378 moles of base. So which is greater, the moles of the acid to start or the moles of the base to start? In this case, it's the moles of the acid. And since acid is greater, we are before the equivalence point. So we're going to need to subtract the moles of the acid to start minus the moles of the base. So now I'm down here. So moles of the acid is 0.00252, and I'm going to subtract the moles of the base. And the reason we do that, 52, hold on, I'm going to find that number for you, 378. So we have 0.12174. The reason we do that is because it is a one-way reaction. When you have this weak acid and you're reacting it with the strong base, it's a one-way reaction that makes water and conjugate base. So because it's a one-way reaction, we do not have an equilibrium here. We don't go backwards. We are consuming the H pluses to make water. And because of that, we have consumed that acid, and we need to then shift the equilibrium in order to re-equilibrate, reestablish that equilibrium. Now, the moles of the base are going to be equal to the moles of the conjugate base. So let's see, I have moles of acid here, and then 0.12378. That will be the moles of my A minus. And it looks like we're not going to be able to simplify, but I'm going to run this both ways. So if we use the Henderson-Hasselbalch equation, then we would have pH equals 4.74 plus the log log of the ratio of the A minus over the HA. And then you should be able to calculate the new pH. So 4.74 plus the log. Make sure you put this into your calculator correctly. So I get a new pH of 4.39 after 6 milliliters of base has been added. Now let's do this the long way. So if we have our acid, and we need to do this in molarity, and because we need to, well, I have this handy chart down here. Why don't we do it this way? Because we need to find the molarity, we need to have the total volume, and the total volume is 30 milliliters now. So my new initial molarity of acid is going to be my excess acid here, 0.00174, divided by 30 milliliters. And I get a new molarity of 0.058, and that is my acid. I have none of this because I've consumed it. My moles of conjugate base were the same as the moles of the strong base. I'm going to divide that value by my total volume. And I can't seem to get that one in my calculator. 0.12378. So I get a molarity of conjugate base of 0.026. That makes sense. So now I'm going to change. I'm going to take some away from my HA so that I can give it to my H plus and my conjugate base. Now I'm going to fill in the Ka, and I'm going to go through the quadratic expression. So you see, this is it's valid to simplify. In this case, going the long way with the quadratic equation yielded approximately the same answer. So it is appropriate to simplify here. So that was C. The pH at 1/2 of the equivalence point. Well, since I needed 19.4 milliliters to get to the equivalence point, 1/2 of the equivalence point is going to be half of 19.4 milliliters. So whatever that would turn out to be, or 9.7 milliliters of the strong base, NaOH, being added. So let's figure that out. Now we know we are before the equivalence point again. This time we have 9.7. So let's erase a bit of this. And we're going to do this over again. Well, we're going to need that. We don't need this one. We're going to do this one differently. So if we have 9.7 milliliters .097, that makes more sense, liters, and the molarity was 0.130 moles per liter. Then I have 97 times 0.13, 0.001261, and I know that's too many significant digits. Hold on. Moles of my base. Now I still have more moles of acid than moles of base. So I subtract my moles of base from my moles of acid. So 0.00252 minus 0.001261. And I get moles of acid in excess. I have 1.259 times 10 to the negative 3. And let's see, the moles of the conjugate base then are equivalent to the moles of my strong base. So 0.001261 moles of OH, not OH, A minus. So I'm going to use the Henderson-Hasselbalch. So pH is equal to pKa plus the log of the ratio of the A minus, which is 0.001261. And I can use moles in Henderson-Hasselbalch, that's all right, divided by the moles of the excess acid, which is 0.001259, this one here. So I take, pKa is 4.74, and add that to the log of 0.001261. Divided by 0.001259. So the log of that ratio, and that's approximately 1. So pH is equal to pKa is equal to 4.74. So the pH at 1/2, the equivalence point, is 4.74. So what is the pH at the equivalence point? Well, we have a different set of, that was too fast, different set of things we need to do. So at the equivalence point, the moles of acid to start with minus the moles of the base added will be equal to 0. But the moles of the base will still be equal to the moles of the conjugate base. So at this point, the moles of my base, going back up here, 19.4 milliliters of that base. So I'm going to calculate that. 19.4 liters times 0.130 moles per liter. I need to know how many moles that is. And that is moles of the conjugate base, 2.522 times 10 to the negative 3rd. So that goes here. I need the total volume of solution. Well, at the equivalence point, I learned that I needed 19.4 milliliters of base, and I'm talking about a 24.0 milliliter sample of acid. So I add those two things together, and I get 43.4 milliliters, which as converted to liters is 0.0434 capital L liters. And I'm doing this so that I can get the molarity of my conjugate base. So 2.522 times 10 to the negative 3rd divided by 0.0434. To get my molarity of conjugate base, I get a 0.0581 capital M molar. Now that's going to go right here. Because we have consumed all of that weak acid. We have consumed all of that strong base. So what we have done is pushed everything over to the conjugate base, the A minus. And because everything is going to be dependent on A minus, it's going to be the reactant now. And when it's the reactant, then we're focused on the Kb, not the Ka. So the Kb is related to the Ka by Kb is equal to Kw over Ka. Remember, Kw is defined as 1 times 10 to the negative 14 at normal conditions, 25 degrees Celsius and such. So we need our Ka value of 1.8 times 10 to the negative 5, and we're going to divide Kw by that value. So putting that in your calculator correctly, hopefully you should get 5.5, I'm going to round that, 5.56 times 10 to the negative 10. So that value goes here. Now we have no initial value of this. We need to change this by some value x. We don't know x yet. We're going to calculate it. It's not going to be tough. Now, notice how our initial concentration, 0.0581, is much more than 1,000 times greater than our Kb. So we can simplify this. Now, to simplify it here with a Kb that does not mean Henderson-Hasselbalch, that means we can do this. And when we do that, we solve for x first by multiplying both sides by the denominator, 0.0581. To get x squared is equal to 3.2, I'm going to call that 3.23, times 10 to the negative 11, but that is not your answer. You then take the square root of that value, and I get 5.68 times 10 to the negative 6 capital M molarity. So now you have to know what that X value represents. Now, it is not the hydrogen ion concentration, it is hydroxide. So to solve for pH, it's my opinion the easiest way to do that is to solve for the pOH because it's already in your calculator, just punch log. So the pOH for this concentration is 5.25. I'm going to round that. And then the pH is then 14 minus pOH. So I get a pH value of 8.75. So that is the, there it is. That is the pH at the equivalence point for this solution.